We are going to pick up where we left off in the last lecture. Having said that, I do want to make a point really quick before I get into all of this. When I went back to edit the lecture video, I noticed you couldn't hardly see the board. And I've noticed this a couple of times that you can't see the board, it'll be blurry or whatever. I need y'all to let me know when that happens. Like whatever that means, I need y'all to let me know. That way you can actually see the material and understand things. But having said that, let's pick up where we left off last class. We were looking at these three integrals. So like I said, these things are called integrals. You can think of them as antiderivatives because they undo the derivative to an extent, right? So we say that that the integral of f of x with respect to x is equal to capital F of x plus c if and only if the derivative of capital F of x is equal to f of x. So with this in mind, like I said, these are just undoing derivatives. So if -5 is the result of a derivative, then our capital F of x should be -5t plus some constant. So for whatever it's worth, and I know I've mentioned it in the past, this IFF is if and only if. It's mathematician shorthand. We have a bunch of things like that, like we'll sometimes write therefore as a triangle with 3 dots. We're just lazy when it comes to writing, I guess. But this problem, looking at the last one here, we know this thing is going to be equal to f of x plus some constant. And what that means is that the derivative of f of x is going to be equal to, sorry, I meant to write these as t's. What that means is that the derivative of this is going to come out to be -5. If that's the case, then the only sort of functions that'll do that are those linear functions of the form -5x plus some constant, right? So we can come up here and just rewrite this as the integral of -5 with respect to t is going to be -5t. I did it again. So in this way, like I said, we're just undoing these derivatives. So really quickly, just jumping to the next slide and comparing, they came to the same conclusion, -5t plus c. Now, with this in mind, why don't we all try to take a minute to yourselves to figure this one out really quick. What you've got is the integral of 3x with respect to x. based on those rules of integrals that we were talking about last class, this thing should come out to be, well, let me write out the rules first, the particular rule. The power rule tells us that anytime we have x raised to the n power, we're integrating it with respect to x, this thing is going to come out to be n plus, or my mistake, 1 over n plus 1, x raised to the n plus 1, all plus a constant. We also had another rule that told us the integral of c times a function with respect to x is going to be equal to c times the integral of f of x with respect to x. So with that in mind, coming up here, we can rewrite this as 3 times the integral of x with respect to x is equal to 3 times 1/2 x squared plus c. Let me make sure. Okay. Hey, folks at home, can somebody say something really quick? I want to make sure that if you are talking, it's going to play through these speakers.
Hello.
Hello?
Thank you. All right, coming from my laptop, but that'll work. All right, so looking now to the solution of this problem we just did on the board. Comes out to be the same thing, right? The first thing they say is to use the constant multiple rule. They suggest rewriting x as x raised to the first, but honestly, I think you just leave it as x. And then apply the simple power rule. You get your solution. So let's go back to these basic integration rules really quick. Just so that we can remind ourselves what all they include, or what all they tell us. So the first one we've got is that the integral of a constant is just going to be k plus, or k times x plus c. The next one is the integral of k times a function with respect to x. This thing's going to come out to be k times the integral of that function with respect to x. After that, we have the sum and difference rules. They tell us that if we have two functions and we add them or subtract them together, and then we integrate, this is going to be equivalent to taking the integral of one and adding it or subtracting it accordingly to or from the other. And now finally, the simple power rule. So the simple power rule has an important addendum attached to it. It requires that our power isn't going to be -1. And if we think about this, that kind of makes sense, right? If we were to take the derivative of this repeatedly, we're going to eventually get to a constant, right? Then when we take the derivative of that constant, we're going to get to 0. And after that, that's where we stop, right? Like there's nothing else that will happen with the power rule beyond, or I mean with our derivative beyond just coming out to be 0 over and over and over again, right? And if we think about all the derivatives we've seen so far, the only ones that come out to be 1 over x or 1 over a function are the ln's, right? They're all the logarithms. So if we're going to think of this integral as undoing the derivative, it would make sense that in the case of n equal to -1, we're going to have something to do with a logarithm, not to do with x raised to some power, right? Make sense what I mean? Cool. So, the general process of solving these integrations. The first thing you're going to want to do is actually write out what your integral is, and then rewrite it in the easiest way to read it. And the reason why we want to rewrite it is so that we can spot rules and where they apply. From there, you want to integrate, and you want to simplify. So having said that, let's check out these two problems. All right, here, we're going to rewrite this. We're going to write it as x to the -3rd, right? So that means we're going to use a simple power rule because n isn't equal to -1. Make sense? Similarly, if we rewrite b is going to be x to the 1/2 power. So again, the power rule, because our power isn't equal to -1 here. So looking at the original integrals, rewriting them, applying those power rules, and then simplifying. So this really is just backwards derivatives, right? This process is identical to how we were solving derivatives. We're just going in the opposite direction now. Okay, so how would we go about solving some of these? How about y'all try A, and I'll do B up here on the board really quick. All right, so for this first integral, did anybody get 1/2 x squared plus 2x plus c? Did y'all get it? Not quite. Well, if we look really quick at how to break this up. First thing, we're going to break this up into two parts, right? Using that sum of difference property. Then we're going to say, hey, this thing is going to integrate out to be 1/2 x squared plus some constant. And this thing, it's going to integrate out to be 2x plus some constant. So if we rearrange these, we're going to have x squared over 2 plus 2x plus our first constant plus our second constant. But our first constant plus our second constant is still a constant. So why don't we just absorb them together and call them both added together c? Now comparing that to this problem, it's going to be the same idea, right? We're going to break this integral up into 3 different smaller integrals. When we evaluate them, they went ahead and just pushed all of those constants to the back. Just went ahead and added them all together here. But then they simplified right after that, right? If we look, same thing, right? I'm showing that in-between step of breaking our integrations up. Another earthquake? Anyhow, so I show the in-between steps of breaking these integrals, this integral up into 3 smaller integrals, what each of them evaluate out to be, and then I reduce it to this point, this point, blah, 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 to this final solution is what I'm trying to say. Make sense? All right, now what about this one? How are we going to handle this? What do you all think? What's the first step here? Well, if we break this fraction up into 2 different smaller fractions, what will happen? This thing can be rewritten as x plus 1 over x to the 1/2 dx, right? And if we really wanted to, we could rewrite it again as x to the negative 1/2 times x plus 1, the quantity, integrated with respect to x. Now we can distribute this all the way through, agreed? This is x to the first power, so when we distribute through, we're going to get the integration of x to the 1/2 plus x to the negative 1/2 dx. Agreed? Now, we can break this up into 2 different integrals to get x to the 1/2 dx plus x to the negative 1/2 dx. Well, hey, our power is not equal to -1, so we can go ahead and apply the power rule, right? The simple power rule. When we do that, we're going to get let's start by actually identifying what n is, right? N is going to be equal to 1/2 here. So n plus 1 is going to be equal to 3/2. Meanwhile, over here, n is equal to -1/2. So n plus 1 is going to be 1/2. Agreed? When we integrate these, this is going to come out to be 2/3 x to the 3/2 plus our constant c. And then this is going to come out to be 2 times x to the 1/2 plus our constant c. We can rewrite all of this as 2/3 x to the 3/2 plus 2x to the 1/2 plus c. So this comes from 1/n plus 1, right? We said n plus 1 was 3/2, so 1/n plus 1 is going to be 2/3. Similarly, this also comes from 1/n plus 1, because we said n plus 1 was 1/2. Well, 1/1/2 is going to be 2. So when we compare, they went ahead and simplified quite a bit, going from here to here. They said simplify it and then factor out terms. They say it's all right to leave it the way it is right now. Because what I want you all to focus on is how to do integrations, not how to do algebra. So now there's a question that I suspect some of y'all are asking, or at least I hope some of y'all are asking yourselves. Why the hell does this thing have to have this damn constant? Because it is wrong without that constant. If you don't have that constant, I will mark it wrong every time. It's got to be there. But why? What is this thing doing? Well, to answer that, let's think about what the derivative does and what it tells us. So we're saying that the derivative of f of x is going to have to be f of x, right? So what does this mean, this derivative? It just tells us what the slope is, right? It tells us nothing about the position, the location of our function. Agreed? And in fact, if we took this one step further and changed our function a little bit, just a little bit, and we shifted it up or down, by adding or subtracting some constant, it still comes out to be the exact same derivative. And this is why you have to have the c. Make sense? Because this c, it tells you a lot about location, and it lets you solve for particular solutions. So here, this problem is asking you to solve a particular derivative with a particular solution. We're saying we've got the derivative of our function that thing's equal to f of x, and that thing's going to come out to be 3x plus 5. And we know that our function at 1 has to come out to be 9. All right. So with that said, we want to find this function. So we're going to integrate 3x plus 5. This is going to come out to be 3 over 2 x squared plus 5x plus some constant, right? Now, what we're going to say here is that this thing, all of it, is equal to f of x. And if that's the case, well, we know that when x is equal to 1, 3 over 2 times 1 squared plus 5 times 1 plus c is going to be equal to 9. So this is going to come out to be 3 over 2 plus, let's go ahead and write 5 as a fraction of 2, so it'll be 10 over 2, right? Well, just for the sake of being concise, let's simplify these two fractions being added together. It's going to be 13 over 2, right? This all comes out to be 9. Well, hey, if that's the case, now we can solve for c here. We can subtract 13 over 2 from 9, right? Well, 9 we can rewrite as 18 over 2, right? So the c, if this is going to come out to be equal to our function, the c is going to have to be whatever solves this problem. Make sense? So whenever you solve an integral, an indefinite integral, because that's what these are actually called, is indefinite integrals. And I'll explain that later. The reason why is because we have nothing for bounds, and I'll explain all of that much later. But whenever we solve these integrals, we have to include the c. Why? Because of all of this. We have to be able to actually find our function. We have to be able to say that, hey, whatever we're getting, its derivative will include all possible, or it will include all possible source functions whose derivatives will come out to be what we're given. Does that make sense what I mean? So just looking really quick, go ahead and type all of this up. What we've got here is we're saying that, hey, we just want to restrict c so far as to make our integral equal to our function. Since we know that our function at 1 is equal to 9, we can solve for c. When we solve for c, we find that c is equal to 5 over 2. And we can now find what our actual function looks like. So if we're given what the derivative of our function looks like, and that our function at some particular x value is equal to something, we can solve for that c. That's all I'm saying here. So what is this c doing? I've already hit on that, right? It's shifting our function up and down. But what does that look like? What does it mean for our integral to be x cubed minus x plus c? It means it is a member of the family of functions x cubed minus x plus some constant. These are all families of functions. They have the same general form up to a constant. So we would say that these are a family of solutions, solving, or whose derivative comes out to be what we were given. And really all this c is doing is saying, we don't know which one of these it is, but we know it's one of these. Some more of the same. The C is really kind of this idea of making room for the right function, in a sense. So, I want y'all to spend about 3 minutes working on this really quick. See what y'all come up with. Here we're given that the derivative of our function is 2x minus 2, and our function, when x is equal to 1, our function is equal to 2. I want you all to spend, like I said, 2 or 3 minutes trying to solve this on your own really quick. Okay, so for this first part, we want to integrate, right? That's the first thing we're going to want to do here. We're going to want to say that f of x is equal to the integral of 2x minus 2 with respect to x. Well, this is going to come out to be x squared minus 2x plus a constant So f at 1 is equal to 1 squared minus 2 times 1 plus c is equal to, this is going to evaluate out to be -1 plus c is equal to 2. So c must be equal to 3, right? All I'm doing here is adding 1 to both sides. And if that's the case, then our function must be equal to x squared minus 2x plus 3. Now let's double check that. 1 squared is 1 minus 2 times 1. 2 times 1 is going to be -2, or I mean 2, so 1 minus 2 is going to be -1, plus our 3 is going to come out to be 2. So what did we just solve for? Well, our integral told us that we can have any of these possible choices of functions, right? These are all of our functions just shifted up. Shifted up by different values. And then we said, well, we're given this initial value where when x is equal to 1, our function is equal to 2. And we solved for what c is. That's the same thing as coming over here and saying, well, of all of these possible choices, only this one fits. That's what we're doing. We're just going to do it mathematically here. So looking at what all of this looks like, integrating, we get x squared minus 2x, just like what we got. We plug in 1 for our x values and set all of that equal to 2. And then we solve for c. So what do we think? How does this sit with us? Process makes sense? It's going to take a couple times to remember it, right? So the way to remember this is to start with what you know. You know you're given a function's derivative, right? And you know that you're going to be given the function at some particular x is going to be equal to some constant, right? So knowing just that, you're going to start off with this, right? Well, integrating this is going to give you an idea of what your function is going to look like. And then you can use this to get an exact idea of what your function looks like. So the process is really just a process of elimination, working backwards from what you know, what you're given. You know the derivative. If I undo the derivative, I apply the antiderivative, I get a family of functions. And if I apply a particular value, I'll get the exact function. So As another example, we've got a ball that's being thrown from a cliff. Is that what it was? Yeah. All right, this one's going to be a little bit more involved, but not so much that we can't figure it out. What this problem is doing is saying you've got a ball, it is thrown upwards with some initial velocity of 60 feet per second. So we know that velocity at time equal to 0 is equal to 64 feet per second. That's supposed to be an ft, not an f. You know the initial height is 80 feet. What else do we know? What do we know about things that are thrown, dropped, whatever? Gravity applies to them, right? So we have to worry about an acceleration. We know that acceleration due to gravity is equal to 32 feet per second squared. We also know a couple other things. From earlier in the semester, we saw that the derivative of our height function was our velocity function, and the derivative of our velocity function was our acceleration function. So if I undo this derivative, I'm going to get velocity as a function of time, right? Okay, so let's do that really quick. Let me actually write a note here. This implies that the derivative of acceleration with respect to time is going to be equal to our velocity function plus some constant, right? And this up here is going to imply that the integral of our velocity function with respect to time is going to be equal to our height function plus some constant. So knowing that, we want to integrate this. So this tells us that the integral of 32 with respect to t, this thing's going to come out to be 32 times t plus some constant. This is equal to a velocity function. But hey, at time equal to 0, the initial velocity was 64 feet per second. So plugging in 0 for t, we get that c is equal to 64 feet per second. Let me write it this way. So we just found our velocity function. This is going to be 32 times t plus 64 feet per second. And this is 32 feet per second squared. I'm actually going to erase the constant for now. All right, so we're going to play the same trick, but this time we're going to try to get the height function. So this is going to tell us that 32t plus 64 integrated with respect to time, this is all going to be equal to 16t squared plus 64t plus some constant. This is equal to h of t. But h at time equal to 0 is equal to 16 0 squared plus 64 times 0 plus a constant is all equal to 80 feet. So altogether here, we get then that height as a function of time is equal to 16t squared plus 64t plus 80. Now let's compare that solution to the answer. Looking at the book does in fact come out to be the same thing. Height, I forgot a negative all the way through here. And I apologize about that, everybody. This should be negative, 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 negative. Because acceleration's in the opposite direction of velocity in this particular case. But comparing, like I said, other than that negative, they're the same thing, right? So jumping to the solutions, we know that height at time equal to 0 is 80. We know that velocity at time equal to 0 is 64. We know that the second derivative, that is acceleration, is negative 32. Again, that's because these were in opposite directions, right? If we're accelerating due to gravity, we're accelerating downwards, they were throwing the ball upwards. So however we solve this, this should be in a negative, or these should be negatives. So one way or the other, the signs we're going to have to flip. It's just about relative to how you want to look at the problem. But anyhow, so knowing that acceleration is equal to negative 32, you can solve for velocity. We're given the initial velocity, so we can solve then for C and get the actual function for velocity. We're given the initial height. So playing the same trick, we can solve for the actual position of height. The actual function of height. And they just point out, hey, we can factor things out. Clean this up a little bit. And solve for the particular questions that might or might not occur. So, having said that, what time is class out?
6:50.
6:50, that's what I thought, okay. Having said that, we'll let y'all play with this problem for a couple seconds. What we've got is the derivative of cost with respect to demand, right? So that's marginal cost. My mistake, it's not with respect to demand, it's with respect to the units of product. So what we're given erasing all of this. (32 minus 0.04x and we know that C at 1 is equal to $50. So for this problem, what we're going to do is we're going to integrate, right? We're going to say, cool, let's find out what 32 minus 0.04x is. When we integrate it, this thing's going to come out to be 32x minus 1/2 0.04x squared plus C. And I'm actually going to change that to K, just so we don't confuse everything here. Plus K. So now we're told, well, first, that uses this first part. Now we want to use this part. We're told that C, the cost function for 1 unit, so that's 32 times 1 minus, we can simplify this a bit to be 0.02. 0.02 times 1, that squared, plus K, all comes out to be $50. So we subtract 32 from both sides. And then we add 0.02 to both sides to solve for K. And this is what it comes out to be in the end. And checking really quick, we throw 1 in, we're going to get 32 minus 0.02 plus 18.02. Well, these two 0.02s are going to cancel, so it's going to be 18 plus 32, or just 50. So it does in fact check out. And now we can go ahead and calculate what the price is for producing 200 units. I'm not going to do that on the board, but I am going to jump to the slide to show how we work through everything again. We integrate, solve for K, put it all back together. And that's it. That's the process. Integrate, solve for K, put it all back together. Now, jumping into section 5.2. Section 5.2 is going to start off with a more general rule for the power rule. And I'm going to go about this slightly different. I think it'll be easier to show this another way than just to give you all this rule. All right, so let's think about what this is asking us to solve. This is saying we've got some function u of x raised to the n, right? We took the derivative of this thing. Well, it would come out to be n times, here actually just to keep with the powers, I'm going to raise it to n plus 1. N plus 1. This is going to come out to be n plus 1, our function, raised to the n plus 1 times the derivative of the function. So moving backwards then, if we get something that looks like this, when we integrate it, it should come out to look like this. How are we going to recognize all of that? That's the question. What would all of this look like on paper? Well, one example of what we've seen in the past might be something like x squared plus 4x raised to the 1/5. Let's go with third. Well, this is going to come out to be 3 times x squared plus 4x squared times the derivative of what's inside, so that's going to be 2x plus 4. So if we're given this and asked to integrate it, so let's say we didn't see how we got to this part, right? We want to work backwards now. We're told integrate 3x squared plus 4x, that quantity squared, times 2x plus 4, respect to dx. If your first response is not, oh, hell no, I don't know why, because that's my first response. But hey, notice something here. This thing here, well, it looks like the derivative of this thing, doesn't it? And in fact, having gone through this calculation, we already know that it is, in fact, the derivative. So why don't we, for right now, rewrite this as u, and rewrite this as u dx. Or I mean du dx. I'm going to say u is x squared plus 4x du dx. Well, this is going to come out to be 2x plus 4. Well, if we look at it this way, then we can rewrite this integral a little bit. We can rewrite it as 3 u squared du dx integrated with respect to dx. Well, this is calculus, and we know that it doesn't actually work this way, but we can kind of think of these differentials as canceling each other out. And if that's the case, then this is kind of like 3u squared du. Well, if that's the case, then this integral, it's going to come out to be u cubed plus c, right? We just said u is equal to x squared plus 4x. That's actually equal to x squared plus 4x, that quantity cubed, plus a constant. And if we look at where we started, it is in fact the same thing. What I just showed you is what's called u substitution. I talk about it a little bit more in one of the future slides. But that is where this idea is coming from and what it's trying to tell you to do. Is it's trying to tell you, if you're given a horrendous looking rat's nest of an integral, if you can identify a u, and you can identify its derivative, then you can rewrite it in this sort of a way. Think of it in this way. Does that make sense to everyone? Folks at home, does that make sense?
Yes.
Yeah?
Yep.
Cool. So just as a couple examples of what these problems might look like. Let's look down here first. This looks nothing like what I just wrote on the board. But we can rewrite all of this. We can rewrite everything in that problem. So let's start there. So we've got the integral of negative 4x over 1 minus 2x squared, that quantity squared, integrated with respect to x. I'm going to rewrite that integral sign. We can rewrite this. Done it a dozen times. We're going to do it a dozen more times. We're only going to keep doing it till the end of time. We can rewrite this thing as negative 4x. We're going to put that inside of its own set of parentheses just for now to hold on to it. Times 1 minus 2x squared, that quantity raised to the negative second power, dx. Well, hey, looking at it this way, something jumps out now. This thing and this thing looks like they might be related. In fact, this looks like the derivative of that, doesn't it? If we say u is equal to 1 minus 2x, that quantity squared, then du dx is going to be equal to negative 4x. So because of that, you can now rewrite this as u to the negative second power du dx integrated with respect to x. Well, that's like u squared du, right? Well, if that's the case, then this is going to be equal to 1 over negative 2 plus 1 all times u the negative 2 plus 1, all that plus c. Rewriting it, we get negative u negative first power plus c, or substituting everything in now, negative 1 over 1 minus 2x squared plus c. Everybody cool with this? So really quickly, let's jump and look and compare answers. They do the same thing, right? They pull up the denominator by making the exponent negative. So we've got this negative 2 power, we've got everything inside of it. This thing is something raised to a power, and that's what they're really trying to tell us here, is to identify it by using something raised to a power. Looking at that something raised to a power, we can say, hey, let's set that equal to u, then we do in fact have a du dx right here, right? Rewriting then our integral, like how I did, we can solve the integral. What they're doing here, they just went ahead and subbed u back in. Instead of rewriting it like this, we just went ahead and substituted it back in right after the integration. And then simplified it from there. I would suggest simplifying it and then putting your substitutions back in, just because it's easy to lose something when you have a lot of stuff, right? And using this u condenses everything you've got to write. So there's less to keep track of. Having said that, that is time, and I will let you all go. If you all have any questions, I'll stick around for a couple more minutes.